Okay, so this is going to be the first of what's probably going to be a couple videos where I work out this formula right here. It's called variation of parameters. I'm doing it for a 2x2 system with a input. Sometimes it's called a monkey, that f of t, to find the xp for that. I'll go over what all these different parts are, but I want to put that formula up to start. So your warm-up / anti-set is to multiply this these two square matrices right here. You should know how to multiply matrices from before. Remember, you go across and down, top left, across and down, top right, bottom left, bottom right. You will get a square 2x2 matrix. So pause, do it. Okay, so you should get that. The 5 and the 4 come from 1 times 5, that's 5, plus 4 times 1, 5 plus 4, and then so on and so forth. So, boom, that adds to 9, 10, 13, 10. Okay, so that's round 1 of the anti-set. Next round is going to be related to the system that I'm going to put up in a moment. So I'm going to take x prime equal negative 3x plus 2y plus 4 e to the negative t, and y prime equals 3x minus 4y. This should not be there. Okay, so first thing I want you to do is recognize that you could do this with undetermined coefficients, which you should have learned already. You should know that from earlier. And I can rewrite this thing as x prime equals, I can write negative 3, 2, 3, negative 4 times x plus 4e to the negative t 0. So if you were doing this with undetermined coefficients, you would do your guessing, and then you would like plug it through and then solve for a1, a2 the way that we've learned in class to figure out what would give us that. Now there's a problem in this one that I've given you here. That doesn't work. We've avoided these thus far. So we kind of you would run into a jam if you tried this with undetermined coefficients. So the next part of your anti-set is to treat this as A and find the fundamental matrix for this thing. So X, the fundamental matrix, equals what? Remember, you do eigenvalues. Eigenvectors are the same way we've been doing all along, and you just smash them into a square matrix. So go ahead, pause, do that. Okay, so hopefully you agree with what I have in red here. I take this matrix A, I find the characteristic equation, negative trace is 7, the det comes out to be 6, factors to this, gives me two different eigenvalues. When I do the 6, I get these guys. The vector that goes with that is 2, negative 3. When I do the negative 1, I get these. The vector is 1, 1. So I switched them here from the way that they're written here because I was like, I like having that guy first. So it's this 1, 1 times e to that vector as the first column, and then 2, negative 3, 2, negative 3 times e to the negative 6t in both of them. So that's fundamental matrix, or sorry, I should say that is a fundamental matrix. There are an infinite number of possibilities. The second most obvious one would be to flip these two columns. I could have a 10 and a 10, whatever. I like to keep it as simple as possible. So hopefully you agree with that. Next layer of your anti-set is to find the derivative of the fundamental matrix. So find x prime with respect to time. You just derive each individual piece with respect to time. So go ahead, pause, and do that. Okay, so hopefully you remembered all your chain rule and everything like that. This and this, they're both the same thing. They're both derived to negative e to the negative t. This, I take the negative 6, multiply it out front, get a negative 12, e to the negative 6t, and then this pops, gives me a positive 18, e to that. Hopefully you're good with that. Here comes the next round of your anti-set. I would like you to, hold on. Okay, so you may remember what I asked you to do at the very beginning was to multiply these square matrices. That was sort of to get you ready for what I'm about to ask you to do now, which is the next layer of your anti-set. I want you to take this fundamental matrix right here and multiply it by the original, or multiply it on the left by the original matrix that we started with. So I want you to multiply A times X. I will remind you that A was negative 3, 2, 3, negative 4, and X, I'm just going to copy this line, e to the negative t, e to the negative t, 2 e to the negative 6t, and then negative 3e to the negative 6t. And you should see something when you do this, right? Like there's a point to this. So go ahead, pause, do that work. Okay, so hopefully you agree with me here. I haven't simplified yet. This line right here comes from this negative 3 times the e to the negative t. I'm going to go across and down. That's this product. Plus 2 times e to the negative t, 2 e to the negative t, and so on and so forth. This times this is the bottom row. This times this is this row, or is this entry. And then this times this is this entry. So you may already notice this, but what do I get when I do, notice they're both e to the negative t terms, all the like, I can combine like terms. Negative 3 and 2, well that adds to negative 1. 3 and negative 4, negative 1. Negative 6 minus 6, negative 12. Notice they've got the same exponent. 6 and 12, 18. So what I want you to see is that these two lines are the same. That's going to be true for every fundamental matrix that exists. X prime, if I derive the individual components of a fundamental matrix, it's going to give me the same thing as what I would get if I were to take the original matrix A and multiply it by X. That's one of the key things that I'm going to use to prove that variation parameters formula up top. So you should put a big box around that, and we'll save it for later. Okay, the next thing I'd like you to do is to find the determinant of this fundamental matrix. So that should be pretty simple. A det is just this product minus that product. So I will pause again. I want you to find that det. Or, sorry, I want you to pause. I want you to find that det. Okay, so you should have this, boom, boom, which gives us this, which gives us this. Now, all right, so hopefully you have this here, which gives us this and this. I don't really care about what the thing is here. I don't care what that is. What I care about is what it's not. It is not 0. I would argue that any fundamental matrix that you found or any eigenvalue work that you've done, if you were to do this det, it would always not be 0. It can never be 0. Let me explain briefly why that has to be true. I'm not going to prove it, but I'm going to make an argument for it. Well, think about it. These eigenvalues, this -6 gave me this specific pattern, which gave me a 2 and a -3. Then that eigenvalue -1 gave me the pattern we're at a 1, 1. This and this will never match for two different eigenvalues. Now, we haven't talked about a repeated eigenvalue, but it does work a little bit differently. So, I mean, like, what I'm saying here also holds true, I guess. Anyway, like, this and this are never going to match. And what I would argue is that for the determinant of the fundamental matrix to be 0, this piece and this piece would have to be multiples of each other. They would have to be, our big word, linearly dependent. This is linearly independent from this. They're not multiple. They can't be constant multiples of each other. Because when I do this product minus this product, say I had a 2 and a 2 there, well, then things would zero out. But that would mean that this would have the same eigenvectors, and that's impossible. And I think you should see that. I haven't proved it, but I feel like this is a good enough argument for why it has to be true. So, then the next question is, what does that mean if the determinant of a fundamental matrix is non-zero? Well, that goes back to our discussion of inverse matrices. That means that X inverse has to exist. Which helps me out if I'm trying to solve things algebraically. I will use that. You know, I said I would use this guy in blue over there. I would use this. I'm also going to use this piece right here. Both of those are super important for how I'm going to prove that variation of parameters formula. All right, so I'm going to stop this video here, and I'm going to start up another one that will take us through the second half of what I want to do to prove this formula.